Well, let me bring up the paper, my paper first. Where it is? Hold on. So, all right. So this is a paper I wrote before, and probably you know that before. Okay. This is about the project Ricci curvature. So it took a while. We're trying to figure out what kind of condition we can put on the project Ricci curvature, so it makes sense in geometry. That's a very important. Okay, long time ago, already in the book I already mentioned that quantity, but I never seriously thought about that. Okay, we are busy with other topics. So so what is so-called project Ricci curvature? It's so I have to begin with a so-called projective spray. Okay, so you give a spray G, right? And then you modify the spray G, right? And then using the S curvature. So the S curvature must depend on volume. Okay. Now, in in some papers that people just use just consider fin symmetric. That's fine. Then every fin symmetric you have associated volume form. That's okay. Then you have S curvature. Then you can modify the spray. Okay, the spray induced by the fin symmetric. And if you always choose the volume form associated with the fin symmetric, then you have some you will lose the projective invariant properties. Okay, I will explain to you later. So first of all, you just have a general spray. Then you have a volume form. Then you have a spray and the volume form. You get an S curvature. Okay. Then you modify using that to modify the original spray. So actually trying to get rid of the PYI part. Then that spray is very important. Let me go to the introduction area and the primary area so you can learn. Yeah, let me go to that page first. Okay. So so you modify the spray. So first of all, every spray you have a connections and curvatures, and you got curvatures, right? And then the relationship. Okay. So the spray, yeah. So here's one. So the S curvature, okay, is determined by the spray and the volume form. Okay. Now the volume form, if you talk about spray, there is no associated volume form. Okay, determined by the spray. So you have to have an independent, force you to have independent volume form. Okay, and then use a volume form spray. You can modify the original spray, and that spray is very important. It's called invariant. Okay, it's projective invariant. So when you change it, if you keep the volume, if you change the spray, then you do not change. You do not change the modified spray. Okay, so that means if G1, G2 are projected relative, and then both gives you the S1, S2, but S curvature. But as long as the volume is fixed, then the corresponding G hat will be the same one. Okay, you're not going to get it different. So that's a good part of that. Okay, that's good part of that. So using the volume form, using the spray, then you can define Ricci curvature and of the modified spray. Okay, G hat, and that Ricci curvature we call it projectively, the project Ricci curvature. Okay, so the reason is it's project invariant when you change the spray projectively. Okay, and with the volume form fixed. Okay. And how do now the so-called project Ricci curvature is defined to be the Ricci curvature of the G hat, but you can also express it related to related to the original spray, okay, and their curvature. So you by simple computation, you can get equation 3.14. Now, if you change the volume form, you will change the spray G hat. Okay, of course you will change the corresponding Ricci curvature. We call the project Ricci curvature. So there's a couple of relationship. That's related by this. There's two. When you change it, that's related by this equation. Okay. So when you change the volume form, you just change the function. Okay. You just multiply the volume form by a scalar function. So then this two project Ricci curvature, if the volume form change, spray is not changed, okay, then the project Ricci curvature will be changed. Cannot. Okay, that's important. Okay, so I just said that if you keep a volume form and the spray changes projectively, you don't change the project Ricci curvature. But if you fix the spray, changes the volume form, and they're related by this equation 3.16. All right. So the question is, what is the natural condition we can assume on the metric on the spray? So we give a definition. Okay, this is a formula. Okay, 1.2 is already mentioned. Yeah, we give a definition. We thought about it many times, but we give a definition. This will make sense in geometry. When we say a spray is the projective Ricci-flat, if there's a volume form, for some volume form, the corresponding projective Ricci curvature is going to be 0. Okay. Now, why not in the Finsler case? Suppose the spray is induced by the Finsler metric. Okay. Then can I say that there's a volume form? It's independent of Finsler metric, such that the G hat, the Ricci curvature, is going to be the proportional to the Finsler metric. It's hard to explain, but that condition will not make sense. Okay, so I hope you, after you study that, you will understand. So we're not going to give a definition so-called projectively Ricci isotropic, for example. Okay, instead of Ricci-flat. Isotropic means you have to compare with the metric f squared. Okay, so at this moment, just only consider Ricci-flat. Maybe you find out it's modified. Maybe you can introduce a new notion of so-called projective Ricci isotropic. But I don't see that makes sense in geometry. Okay, so that's a key part. Okay, now once you so now next step is to understand the geometry meaning of such so-called projective Ricci-flat spray. And a projective Ricci spray, you don't need to measure the volume, but the definition you have to borrow the volume form to give a definition. But you can talk about projective Ricci-flat for spray only. We just use the volume form to state that condition. The volume form, just there is a volume form. Okay. All right. Now, Finsler metric, when it's we say it's project-flat if the induced spray is a project-flat. So we're not going to use in particular. Okay, from this definition, in particular, if the Finsler metric and it's a Boltzmann-Hausdorff measure, okay, gives a project Ricci curvature. If that's 0, of course it's a project-flat by our definition. Okay. Now, what we proved in this paper is first of all, we're trying to see if an arbitrary volume, how can I check whether this is a projective project Ricci-flat? Right? Given spray, again, arbitrary volume form. How do I check that? Well, it's a projective. It is projective Ricci-flat if we can find another function f such that 1.3 exists. Okay, and that's 3 of the condition equivalent. Then you can also use above formula. You can also just to look at the Ricci curvature of the spray, original spray. Then in other words, a project Ricci-flat means the Ricci curvature of the spray can be written in the form 1.4. Okay, and what is that? What is that theta? That theta is expressed in the form df minus s of s over plus 1. Okay, so so for any volume form, you can find some such function so that Ricci curvature is given in this form. So if Ricci curvature in that form, this kind of spray is interesting. Yeah, so it's not a flat, but it's in taking special form. Okay. Now in the remaining case, what does that mean? If the spray is induced by Riemann metric, that condition tells you, because in that case, yeah, you can. We actually can go to. Yeah, there is a page talking about the remaining case. I just briefly mentioned that in the remaining case, it's a remaining case. So the remaining case, Ricci-flat really means the Ricci curvature of alpha. A remaining metric is called the project Ricci-flat if it is the Ricci curvature alpha is not flat, but it's taking a special form. So in the yeah, this is kind of related to so-called Ricci-Soliton type problems. Okay, but anyway, so that means if you can find a function f, if you can find some function f so that the remaining curvature is taking that Ricci curvature of the remaining metric is taking that form, then and that remaining metric we call the Ricci-flat. Of course, the project Ricci-flat. Of course, the metric is flat. Ricci-flat, then just let f to be 0. Okay, constant, whatever. That's not a big deal. Okay, you can. But this is a more slightly more general than Ricci-flat of a remaining metric. Okay, a remaining metric. Let's repeat again. A remaining metric is a project Ricci-flat, means Ricci curvature of alpha is given by this formula. Okay. So this is about Ricci-flat, and there's also, because of this equation, you can prove that some rigidity theorem. We know that if there's some special case, how can I check if the spray is already Ricci-flat, and but if the S curvature is differential of some function, okay, for some volume, then it's true for any volume, okay? So that condition in the corollary 1.3, it says that if you ask me to give an example, what simple example a spray is a project Ricci-flat. Well, a simple example is if itself it's Ricci-flat, but still not enough. The spray coefficient, okay, and the corresponding S curvature should be almost 0. That means it's differential of some function. Then you can say that G is a project Ricci-flat. Okay. Now the second condition is interesting. Usually people don't talk about that. Yeah, this is about the spray, okay, condition. Yeah, actually the condition of the spray. Okay, for some volume form, if the S curvature is going to be, let's call it exact, okay, df is exact, then for any volume form, it will be exact, okay? So this will be independent choice of particular volume form. But when you talk about S curvature, you have to talk about volume form. You have to use that one. That's part of the definition. So you have to have volume form, you have to have a spray. Then you can talk about S curvature. But a spray, if for some volume form, the S curvature is going to be n plus 1 F0, then this will be true for any volume form. Okay, so that means you can say spray is almost S flat, S means S curvature. Okay, and if S curvature for some volume form, or then for any volume, it's going to be the exact form, one form. Okay, that is a special case, right? And you can easily construct. So, for example, for random symmetric, there are many metrics. It is a Ricci-flat random symmetric, and at the same time, the S curvature 0 with respect to the group of a host of volume form. Then, of course, it is going to be project Ricci-flat such matrix. Okay, so you can give an example quickly. Okay, now 1.4 is it's very natural idea whether this is true when the inverse, right? Now it turns out be if it's project Ricci-flat, if the Ricci curvature of the spray is now negative, then use a standard technique, and you can show that S curvature must be exact for one form. Okay, and in this case, actually Ricci curvature of G must be 0. Okay, so it must be satisfied. It's not like, but for non-complete spray manifold, then this is not true. Okay, and then it's also natural. You can look at the random symmetry, because I already mentioned that how do you construct project Ricci-flat matrix, right? So you first of all you look at where you're trying to find a Ricci-flat matrix, right? Find a Ricci-flat matrix. Then if it's random symmetric, for Ricci-flat matrix, as long as S curvature is 0, then it's guaranteed it is also project Ricci-flat. Okay. But in general, we would like to know what kind of equations can characterize. It still cannot be solvable. Okay, it's hard to describe it. Okay, so by standard computation, a little bit complicated. But we already know the formula for the Ricci curvature of a random symmetric. So using that formula and apply into the details, then we find out it is project Ricci-flat if only if the Ricci curvature alpha satisfies this condition and the beta satisfies the second condition. Now, I have to say that here there's a scalar function h there. Okay, that's just for some h. We don't know. Okay, that function just for some function. Okay, so this is about the paper. The idea, the main purpose of this paper is trying to emphasize a point and introduce the notion of the project Ricci-flat, because I saw a paper before by five people, a couple people there. They still use for thin symmetric only. Okay, first of all, and use the volume form which is associated with the thin symmetric Boltzmann host of one form, and then the corresponding G hat and then its Ricci curvature. You can call it project Ricci curvature, but that project Ricci curvature depends on the thin symmetric only, because the volume form is always associated with the thin symmetric. Okay, then of course you can talk about that metric whether it's proportional to the thin symmetric F. In that case, you can say it's project Ricci isotropic, but the geometry meaning of that, it's not clear to me, because when we talk on projective, project means literally project invariant. It must be invariant under the change of the projective, under the project change. So that Ricci curvature of a thin symmetric is not going to be project event, unless your project event, project change also these preserve the what? Preserve the volume form. Okay, that's unlikely happens. Okay, now after that, what we can do, right? Go beyond the randoms matrix. We can look at general alpha beta matrix or just the alpha beta matrix, right? If you look at the alpha beta matrix, there's still a problem because we have a paper long time ago. We're trying to just talk about Ricci curvature, not the project Ricci curvature, okay? Just Ricci curvature of a alpha beta matrix. The Ricci curvature of alpha beta matrix it is rich isotropic, then you can show that it must be Ricci-flat. Then you stop there because Ricci-flat, its equation is very complicated. Okay, just alpha beta matrix which Ricci-flat. How do you talk about, right? Okay, then and similarly, you can do for the alpha beta matrix. You can do you can work on the problem. Yeah, alpha beta matrix. Sorry, first of all, alpha beta matrix Ricci-flat without any other condition, and you cannot classify them so far. Okay, but with some special conditions, okay, you can show that like a Douglas type. You can show that it must be a square matrix. Okay, right? Remember that, right? So that then you can similarly consider for alpha beta matrix, you can also consider project Ricci-flat alpha beta matrix. Okay, and that I don't expect you can solve it. Maybe a little bit easier the equation, a little bit simpler, like our case here, for randoms matrix, right? The equation is a little bit simpler, So for the for alpha beta matrix, project Ricci-flat ones, I don't remember somebody did that. Okay, but I think this is probably someone should write a paper on that. Okay, but hopefully you can determine that. That's great. If you can determine the equations in simple form, that will be much better because project Ricci-flat alpha beta matrix equation is very complicated. We only have some special cases we can classify it, but in general case, they're not. I don't think so. We can. They are very complicated questions you can get. Okay. Okay. So this is the question. If you know somebody that, let me know. Okay. So you can. So the question is how to classify, determine project Ricci-flat alpha beta matrix. Okay. Now more general alpha beta matrix, even more complicated. Well, I want to talk about this too. So you may heard about, you may hear about alpha beta matrix, general alpha beta matrix, then even a little bit more general, right? Warp product matrix, special type. So in that direction, technically can derive some equations to characterize project Ricci-flat matrix. So I'm going to talk about another paper. Someone did that, but I'm not sure. There's maybe there are lots of problems, lots of area can be improved. Okay. So let me bring up another paper. Yeah, let me stop sharing and share with. Okay, this is another paper. Okay. Okay. All right, so the title of this topic is called the General Spherical Symmetric Thin Symmetries and Projective Quantities. This paper is written on February 23rd, 2020 by someone, okay, by someone. All right. So in this paper, they say that discusses special projective invariant quantities, projective Ricci-flat, usually should say projectively Ricci-flat, okay, not project, yeah. Otherwise called project Ricci-curvature, then project, yeah. Well and doubly quadratic, and there are interactions on general spherical, symmetric, thin matrix, okay. And so what does that do? Okay. All right. So this is the introduction, the paper, and basically, just say what is the instant matrix mean, okay, and why it's important, okay. Then the focus on rich curvature, okay. There are some papers also mentioned, and okay, and if the matrix is a pseudo immanent matrix, okay, they also mentioned the other papers in physics. Okay. So, here's the point. So talking about the Hausdorff. Hey, where's my pen? I'm trying to. Yeah. Okay. Close it. All right. Yeah. Now I would, yeah. Then I when I see this paper, I had to see immediately, what is S curvature mean here? Okay. So in the paper, you will see that the introductions are were written here. Okay. First of all, say it can be naturally considered the non-linear quantity S curvature and the rich curvature deduces another geometric quantities. Okay. And other geometric quantities. That's wrong. Okay. So English is not good enough. Okay. So projective spread associated with a spread on a manifold is given by that. The S denotes the S curvature of a G. That's wrong. Okay. S. Okay. Spread cannot. Okay. Spread cannot determine the S curvature. Okay. So that's. But I will see later. Okay. What's wrong? Okay. Yeah. And then of course you get the formula, relationship between the G tilde and Ricci curvature G tilde and the G, right? So that's already mentioned that. Okay. Then the concept of project Ricci curvature is introduced in the book actually. So it's called a P Ricci curvature. Okay. So a project Ricci curvature is a project event. I know that for the fixed volume form. Okay. All right. So the point. Okay. After that, I think the first person after we did the paper, we have a paper on the Ricci curvature. Then no, actually we try to construct the Ricci-flat matrix. Okay, and then I use a so-called warp product matrix. So warp product matrix was studied recently by many people. I think that I have remembered to my best knowledge. After our paper was Chen Ping and Zhao Lili, okay, I think Mo and his student work on that, okay, and then there's also another paper by Qiu Chenghui and his student. on the projective flat width. Okay, so the matrix studied by then later on actually and Lieben and his student. Okay, studies so-called this is a type of a matrix. Okay, they want to consider. Okay, so here F is written in R and USVT. Okay, and this is a kind of a special warp product matrix. Okay, so it's a spherical matrix. It's a general spherical matrix. Okay, so it's in the form. It's not warp product. Okay, so this is a when you look at I'm sorry. This is generalized. It's a generalized matrix. Okay, so general spherical matrix. So what is so-called general spherical matrix? And general spherical matrix, yeah, it's it's different from can be written as warp, but it's different from warp product matrix. Sorry. There are some examples. Can be viewed as so-called general spherical matrix. It involves a constant A. I think the first example was about the random matrix, a function matrix on unit board. It's projective flat, a constant curvature, a negative constant curvature. And then the most general form involves the vector A. Okay, that's the first example. Okay, the first example shows up in the paper on the classifying of a projective flat random matrix with constant curvature. Then it's natural to generalize it, which you can read in the form like this. Okay, this is type of matrix. Okay, F R phi U S V T. R is the norm of Y, U is the norm of X squared, S is the standard one. Okay, but the V and T additional terms. Okay, V and T, those are when A equals 0, V and T are both 0. So you allow V and T to have here. And I think that did not mention the paper. I think the first paper, I remember Chu has a paper with his student. Okay, consider this type of matrix. Okay, also. Okay, and besides Lee and his student Liu. Okay, so question is, this type of matrix are more general than spherical symmetric matrix, right? If it's spherical symmetric matrix, V is going to be 0. Yes, it's not warp product. By mistakes. Okay, so this type of matrix is computable, a little bit more general than the spherical matrix. Okay, and spherical symmetric matrix. So you have 2 additional vectors here, V and T. 2 additional variable. Okay, V and T, not just only I and S. Okay. Otherwise just call it R, U, and S. Okay, so let's look at this. This is a matrix. Now, in this paper, okay, they got some equations to characterize this type of matrix. Okay, of course it's complicated. Okay, but let's see what kind of equation they can get. All right, so you have so many quantities I and R1, R2, R2, R3, R6, R7, and there's also have some quantity. Let's understand those quantities. This equation, of course, it's almost impossible to solve it. All right, now the sigma. I believe that sigma is going to be the coefficient of the volume form. Now, it's not very clearly stated here. That's the better part of the paper. Okay, sigma it's not a clear state. When at least here I've mentioned that the project rich curvature, it involves the volume form and the metric, okay? And at the very beginning, before the paper, before the statement of the theorem, okay? Otherwise, you have to mention that in the statement theorem. Otherwise, if you look at the statement theorem, okay, it shows up a listing in the appendix. That's okay. I and the Q a listing in appendix. That's fine. Usually don't list in appendix. Okay, shouldn't. Appendix means this is appendix can be removed as you want. Okay, so when you write a paper, yeah, don't give the definition quantity in the appendix. Okay, don't yeah, in the appendix. Okay, and also all the quantity shows up in the paper should be mentioned. Okay, and okay, so G R2, R3 are defined in 3.1, 3.4. That's okay. And the second part says in appendix, listed in appendix for the paper. This is 4, right? Reference is 4. I think reference 4 is the least paper, I guess. Okay. All right. Right, so we are going to look at first. Let me jump to 3. Yeah, we'll go back. Let's see. Go to 3.3 and 3.4, 3.7, 3.8. I'm going to quickly switch to this area. All right, so here's the formula, right? Wow. Okay, as you can see. Okay, and I want to make sure there are all the functions for U, V, and ST, right? Now I still don't see the G, the sigma. Right? So that's the bad part, you see? And it's defined here. I'm searching for the sigma, but sigma is not there. Okay, so so that's why this statement is confusing. The G, okay, what is the sigma? Never mentioned that, right? So you have to guess. Not everybody are familiar with, right? So and the Y depends on U and V, right? Okay, and what is that function? Okay, okay. What is that function? So there, when you start to read the paper, they find out many problems there. Okay, let's go back to see. I'm trying to find out where's the sigma now. Okay, it does not mention any place. Okay, and even the sentence here, S curvature denote is a spray. S denotes the S curvature of spray. That's wrong. Okay, that's incomplete. All right, so my guess is sigma. That's the usual notation for the coefficient of volume form. Okay, so R2, R3, R4, R6, R7 are given in those 4 equations, but G is not. Okay, and he does not explain to what is G. Okay, and it's a huge equation. Okay, so Q. So general spherical metric. Of course, this result including the spherical metrics. Okay, now spherical metrics. I'm not sure nobody even done that. Okay, for project rich curvature, I have to double check. For otherwise I have to mention this including spherical symmetric metrics on the project Ricci-flat ones, right? Okay. So let's see. Continue. Okay, those are the now. It's better to give some solutions. Okay. Now, polynomials. Okay, that's good. So they assume it's polynomial, trying to find the solutions. Okay, trying to find the solutions. Polynomial. The polynomials of degree k with respect to s and t. So now, so this is another issue here. Okay, so that means q. Okay, so it's confused too about. So q means origin depends on 4 variables. That here assume that q depends on 3 variables and r depends on 3 variables. Right? Clear, right? Not only depends on 3 variables, it's a polynomial in S, another one polynomial in T. Okay. Now this part, I think they should at least say, assume that independent of, for the Q independent of T, for R independent of S. Okay. Otherwise, they will say, oh, do you forget, forget T, right? And or forget the S. In that case, they find out in that particular case, it's project Ricci-flat means it must be Douglas. That's a little bit weird. Okay, I have to be honest. How can you jump from Project-flat to Douglas? That's the questionable. This thing, whether it's true or not, based on my observation. I never see a problem like that. If it's if it's Einstein, then it must be Douglas. Okay, for general, for spherical symmetric matrix. That's possible. Okay, now, but it's unlikely. It's true. Okay. Well, let's see the proof. It's harder to understand maybe. Yeah. So section, then that jump to, I don't know why I put 2 topics together in this paper. We focus on project Ricci-flat, then don't need to focus on well curvature tensor. Okay. So because they're totally different type of geometry conditions. Okay, so that says that the general spherical matrix, if it is a well curvature metric, if only for phi satisfying equations. Yeah, those equations are simple. It's nice. Those are a nice equation. Of course, R1, R2, R3 probably are still very complicated expression. Okay, but those are simple equations. Okay, so I think that this paper, if it can be well written, should be separated into 2 papers on 2 different topics, but trying to give some examples, if possible, solutions. Then you can each of them has cover different topics. Okay. All right. Let's quickly go through their argument. Why this is this is a definition. See, sigma is here, shows up. So we're pretty sure that sigma, I'm not sure it's independent of symmetric or it's a group of Hausdorff measure. Okay, Boltzmann Hausdorff measure. Okay, so that's just definition of the S curvature. Okay, and what means S curvature is isotropic. Okay, now, all right, for general spherical symmetric, the spread coefficient can be written in this form. That's okay. That's, I'm pretty sure. List in the appendix of 4. Now, what is a paper 4? Paper 4 is okay. I thought it's a lease paper. Okay, so I'm confused about the list of the papers. It's not in the right order. Okay. Okay, it's not in the right order. I don't see Lee and Liu's paper. So you see, okay, oh, in here, project, yeah, 14, paper 14, projected flat fin symmetry defined by Euclidean metric and the related one form. Okay, that's a, yeah, Lee and Liu's paper. Okay, so paper 4 is by two Iranian people. Okay, a class of bare-volume fin symmetrics, Acta Mathematica. Okay, it's important in Hungary, a journal. All right, so that paper has formulas. Let's assume that. So they started to do general spherical metrics on different problems. Okay, so let's go back. Okay, quickly see. Okay, so this is our formula. Okay, so once you get that, you have to compute the curvature, right? And UV are the variables on the base manifold. Okay, so you, okay, that's weird. Okay, so here's the point. They're assuming the volume form is nature invariant under the any rotation. So they're considered a special volume form, not an arbitrary volume form. Okay, the special volume form in that particular form. Okay. And well, that's a dx. That's okay. So volume form is special. Here, finally, I mentioned that the volume form is special. Okay. Then you can use that to talk about S curvature. Okay. Without volume form, you cannot talk about S curvature. Okay. I think this should be mentioned earlier. Consider general spherical symmetric metrics and yeah, I think it's part of it. General spherical symmetrics, okay, metrics. If you put the addition as a conditions, you probably can get equations. But I shall have to say that maybe that's not the best direction one can go, because for the spherical symmetric metrics, even that you get equations, equations simpler, but it's still harder to solve it. Now you have more general one, it's much harder to solve it. Okay, you have more variables. Otherwise, just only two variables. Now you have four. Okay, four variables. Okay, that's not the that's not the direction one can go. Okay, okay. All right. So for that particular volume form, S curvature of the given volume form. Now that sentence is also not perfect. Okay, you cannot say S curvature of that given form. S curvature depends on spread and the volume form. Okay. Okay. And the volume form is given by this formula. Okay, so that's okay. I think the computation should be is true. Okay, the computation is true. Okay, no problem. Okay, then you have to compute the curvature tensor for this. I think the Douglas, it's not necessary to discuss here if we focus on the project Ricci curvature. Okay. Yeah, that should be separated. Yeah. So then you have 10 pages. Paper is fine instead of 21 pages. Okay. Let's look at, I'm going to focus on project Ricci-flat. General spherical symmetric metrics. Okay. So as I predicted, they have to compute the remaining curvature tensor. So remaining curvature tensor here involves more variables. Okay. Than the spherical symmetric metrics. Okay. Okay. As long as you use maple correctly, those are the equations you're going to get. Right? If long as the program is okay, no typos, then you should be able to get it. Okay. So now we can easily obtain the Ricci curvature. After that, we can easily get Ricci curvature. Okay. So the Ricci curvature is given by the three equations, 3.110. So by this equation. Okay. I think the problem is yeah, you have R, U, S, V, T. Oh my God. Okay, so you have four variables of function. Okay, and those are the just partial derivatives. Okay, and transfer the usual partial derivatives to the partial derivative with respect to U, V, I, S, T. Okay, okay, not a problem. Here, I trust. Now, this is a corollary. Okay, corollary just want to get if the function depends on so many variables, G is a spread acting on that function and it's given by the formula. Okay. And that also uses maple to compute. Right now you can prove theorem 1.1 because you want to prove theorem 1.1, you have to compute the S curvature dot. Okay, S curvature dot. The derivative of a S curvature. See, in the future, if you want to study weighted Ricci curvature, it involves a dot of S and S squared, right? And so you have to go through this computation. Okay, then finally you get so complicated terms. Right? So you got this so many terms, right? This part I'm going to skip it because this is used to prove under that condition it is a Douglas type. Okay. Yeah, just under the special condition. So I don't know how to figure out that just by and find out it's Douglas type. Okay, so we oh, that's really very long. Now then it's harder to believe. Okay, it's not a take so many pages. Okay, in the polynomial case, then get all zeros. I don't know why that come up with these two conditions. Okay, then prove of theorem 1.2. Where's the proof 1.1? 1.1 is not prove it. Okay, let's go back. Okay, so 1.2, that's the many pages for 1.2. So under what condition this become Douglas? Now those two conditions are natural or not? I don't think so. Where's the Q and R? Why they have to assume this? Okay, any example to support that assumption? Okay, what is Q and R? Let's go back to Q and R. I still don't get Q and R here. Nope. Okay. See, that's become a headache, right? Q and R here. You see, Q and R still listed in the appendix section. What is Q and R? Okay, it's not mentioned in this paper. That's weird. Okay, PQR. Okay, and it involves 4 variables. At least I have to mention that Q1 in this paper. You cannot rely on other people to find that particular paper, right? Q and I is not even given. That's a really poor written paper, as you can see that, right? I have many critics. Okay, Q and R is not a. Okay, so I even don't see Q and R. Okay, it must be in the same paper. Is POI contains hundreds pages long? I don't know. Okay, it's not no Q and R. Okay, now the proof of theorem is here. By 2.5, so you basically get the S curvature dot, S dot. Okay, so you find the dot, and how to prove that? Okay, once you get the formula for the S curvature dot, okay, then 2.5, 3.9, 3.26 in the equation. What do you mean in the equation? That's English is poor. Okay, to plug them into the equation, right? 2.5, 3.9, and 3.26 into the 3.9. Okay, let's go back. 3.9, 3.9, 2.5, 3.9. 3.9 is S 3.9 is a Ricci curvature. Okay, that's okay. You need 2.5. That is S curvature. They're all put into 1.1. 1.2, yeah, 1.2 is a 1.2 is here. Okay, 1.2. You see, 1.2 is just the formula for the project Ricci curvature, right? So I want to set this to be 0 for some volume form. Okay, project Ricci-flat means this particular project Ricci curvature is 0. That's okay for some volume. Right? Then the argument just short, just one sentence after you compute all those 3 formulas. Okay, which you need the project Ricci curvature. Okay, then the project Ricci-flat if only for 1.4 is satisfied. So project Ricci-flat for, I think this should be dependent volume for some volume form dV. Okay, and then if and only if 1.4. So 1.4 depends on another quantity. That's a volume form inside, and that volume form we also have to assume a special volume form, not an arbitrary volume form. So a general spherical symmetric fin symmetric. So project Ricci curvature is computed, is defined here using not only, using the spherical symmetric volume form, okay, which they did not indicate here. They just assume that's true, but they did not clearly state at the very beginning of the paper, okay? So they're talking, when we talk about project Ricci-flat, it must be fin symmetric and the volume form. But that volume form, the correct definition will be for some volume form, project Ricci curvature is going to be 0. And that volume form in that case is a spherical symmetric, general spherical symmetric. Okay, so that's a little bit more special. It's not the usual sense. Maybe you can prove that must be general spherical symmetric, but you cannot just assume that for the volume general spherical symmetric volume form, the project Ricci curvature is 0. Okay, that's the issue here, the definition of the project Ricci. Yeah, the volume form that take So that's my comment of the paper. The well tensor part shouldn't be in the paper. Okay, I don't know how does that make it into the same paper. Okay, and yeah, more interesting. So let's take a look at examples. The examples about the sample paper. Well, quadratic. Okay, I think it's more interesting here. It should be the project Ricci curvature. All right, that's about the topic, project Ricci curvature topic, and the paper. Okay. So do you know any other results on the related topic? Okay. So this is not okay. I have a comment about this is about the general spherical symmetric matrix. So general spherical symmetrics, yes, you can discuss some. Yes, you can talk about this. Okay, you can after spherical symmetric matrix, you can talk about general spherical symmetrics, and in some cases you can get the non-trivial solutions. I think the very first example was show up in my paper on the on projective flat random symmetric constant negative constant curvature. Then after that, Mo Xiaohuan did some work on on general spherical symmetric matrix. I attended his lectures before in the classroom. Then after that, most recently, just a couple years ago, is a paper by Chu Zhenghui and his student. Okay, but I think general spherical symmetrics. You can write a paper on that, on Ricci-flat matrix, or maybe on constant curvature or project. But you have to find all the references first before you do the repeated work. Okay. Second, in general, it's harder to solve it because even right now, spherical symmetric matrix we cannot solve it. Okay. All right. So another direction one can go is the warp product matrix. Warp product matrix in it's also
管理了你下面你下面关了块二边了。
OK， 还有什么问题 ？Comments?
Can you hear me?
We hear you. Okay.
Sorry.
I unmute all everybody.
Oh, yeah. So, yeah, have you ended your talk?
Yeah, I'm ended.
Okay.
I'm going to.
Yeah, maybe I think the